This information is brought to you by Charles Sturt University.
Hi, and welcome to another video on how to work out the flux. So this is based on Q9 question 8d. So I'm trying to find the flux of a surface which is not a bit of a plane or a bit of a sphere. It's more complicated. In this case, it's a paraboloid. So let's give a rough idea of the picture. So I've got a paraboloid, which looks like a bit of a bowl, essentially. And we're looking at the surface that sits above, so I'm trying to do the shadow above the disk. X squared plus y squared is 1. So if we draw the shadow again, this is the circle. My Z up here. So circle radius 1, essentially. That's sort of the shadow of this particular region. As we've been told. So we know that it's orientated downwards, so pointing downwards, as opposed to pointing up. And I've got a force, so that's the orientation. Therefore, I know what the normal is. No, the direction of the normal at least. The formula for the normal is not exactly clear from my picture. The regions, I'll have to work that out in a second. Then the vector field itself is basically pointing is R, so the X, Y, Z as components. So given a various point, it'd be pointing this direction, or he'd be pointing here. So all of these are pointing well, in the same direction as the normal, maybe a bit of a bad angle, but at least pointing in the same direction rather than going opposite. So the net flux will be something positive, I can say, but that's about it from my picture. So we need to do some calculations. So when you've got a more non-standard surfaces like this, you really need to parameterize it somehow or other. And so in this case, we've defined the function, so the surface is Z, right? We define it in terms of X and Y, so X and Y are natural parameters in this case. So the idea is then to work out the flux integral, and this is my use of notation. I use the letter little s for surface, the surface itself, and S bar for the vector quantity of the surface area. And so if you parameterize it by various letters, it's a dot product with a capital N, which I'll explain to work in a second, times by the differential of those two particular parameters. So the common one we'll do is we'll parameterize in terms of X and Y's. And the reason why we can integrate that is because, well, I've got the shadow here, so I've got my little shadow in the bottom, which is in terms of X's and Y's, and which I can integrate over easily. So therefore I know exactly how those parameters form. You can do mines more in general. It so happens that when you parameterize in terms of X and Y, you end up getting minus the derivative of Z with respect to X, minus Z derivative partial of Y, and 1. Almost. It depends on the orientation. So it can either be pointing up or down. So I don't know what the sign is immediately, but other than that, that's sort of the magnitude of it all. So different parameters give you different sort of things, and so have a look at the formula sheet if you want to see it in general. But this is what it is for X and Y. So in this particular case, then we know that the surface is X squared plus Y squared. So just take the derivatives. So partial derivative, that one gives you minus 2x. Partial derivative with respect to y gives you 2y, so you put a minus in front of it, and the 1 just stays 1. Now we want it, as you can see from my picture, I've just drawn it, and the orientated downwards, I want it to be pointing down. So therefore the normal should be pointing down, but I've got a positive here, so I've got to change that. And therefore, so the normal in this case is equal to the minus 1, so it'll be 2x, 2y, and minus 1. So I'm just making sure that downwards idea, as though the downward orientation. Let's say we work at capital N. And this is not a unit normal anymore, so it's still not being a unit, and nor do we have to, by the way. So you don't have to worry about that, fortunately. But because we've used the sort of non-standard parameters, so it's parameter is the shadow rather than the surface itself, it sort of takes care of it, which is good. Now we'll look at F. So F is the vector R in general, which is basically just saying components X, Y, Z. Now you can write in terms of IJK, so 2xi plus 2yj minus k, and that is correct. I sometimes find it, sometimes it's useful to write that down that way, sometimes it's useful just to write in terms of just the coordinates of it. But anyway, either way, we need to work out the dot product of the two, i.e. what's the component of the vector field in the direction of the normal. So we still need to work that out. And there's the length of n here is the, I guess you call, fudge factor to make sure that the differential works out, or it's the difference in the size between the size of the area of the shadow and the area of the surface. So the difference between the two essentially is this fudge factor that's coming in. So f dot n, the dot product of the two, so 2x and x gives you 2x squared, plus the next one, so 2y squared minus z. And therefore, our integral then is going to be the double integral of this dot product minus z dx dy. Now, just finishing off, now we want to integrate respect to x and y, but you've got a z there. Well, get rid of that. But you're going, hold on a sec. What we're doing, remember, is we're integrating over this surface. And on the surface, we know that z is equal to x squared plus y squared. So we can just plug that in. So this is going to be z is equal to x squared plus y squared. So this is how we can get rid of any z's, unnecessary things we don't really want. So in this case, the integral is 2x squared plus 2y squared. If you set off at 1x squared and 1y squared, you're just left with x squared y squared dx dy. And we're integrating over all the possible values for x and y. And again, as I've got it here, that's really the shadow. And that's going to be that nice solid disk. So a solid circle, and I call it a disk. So radius 1. That's my common notation for it. So I would think of circles as being just the thin edge, and the disk as being the full thing coloured in. Now, you're trying to integrate over a circle. So the key way of integrating over a circle is use polar coordinates. So we're going to use polar coordinates here. There's no point trying to do Cartesian form any further. So you got to say this is a double integral, and just use normal trick. So for polar coordinates, x squared plus y squared is just r squared. So they match up. The differential, dx dy, becomes r dr d theta. Theta r, well, it's just a circle, goes from nothing up to the full radius of 1, and theta is just a full revolution. So anywhere, say from 0 to 2 pi is one way, especially what the angles are for a full circle. Notice that the integrand here is just r cubed, so we can split it up. So it's a separable one, so we can just do since there's no thetas in this middle bit at all, we could factorize that whole thing out. So in this case, it's called a separable double integral. And so the integral from 0 to 2 pi of d theta is just the length of that, so it's just going to give you 2 pi. Integral of r cubed is going to give you r 4 on 4 between 0 and 1. Sub and 0 you get nothing, sub and 1 you get a quarter. And so we're left with 2 pi times y a quarter, or pi on 2 is our final answer. But just stressing, so back to just general strategies, something to help you remember it. You're trying to work out the flux through a particular region. The best option is try to use the high-level one. So dipole divergence theorem is really useful if you can. Certainly if it's a fully closed surface, that's probably a really good way of doing it. But other strategies is if you've got a nice simple bit of a plane, you can just use f dot little n and just parameterize the surface directly and just understand the surface directly. If the surface is getting more complicated, like it is here, parameterize in terms of two other variables. X and Y are the really obvious cases. And once you parameterize that other case, then it's the integral of capital F dot capital N, where this is the sort of formula here for N. And you're integrating over the two parameters, and then you basically, the region of integration is the shadow of those rather than the surface directly. And so the reason why this is a good method is because we're reducing the surface down, so just integrating over just a flat bit of plane, which is we find easier to do normally. So I hope that illustrates so by looking at some of these, the different methods you can use for trying to work out flux integrals. So the real high level ones will be looked at in tutorial 10. So I hope all that helps to understand it and give you a chance of seeing some of these things in action.